In the next subsection, we'll look at suffix arrays. Sounds similar to suffix trees and has relations, but first of all, looks like an entirely different beast. The ultimate goal will be to put our suffix trees on a diet by getting rid of most of the pointers. So here's our suffix tree, the way I've drawn it before in some examples, growing to the side. And what I've done here is put the leaves one below the other. I didn't stress this earlier, but we've actually had that before. If you make sure that all the child edges from each node are ordered by the alphabetic order of the letters, then you actually get all those suffixes in lexicographic order. The dollar comes first because that's always the smallest character in our ordering. Then there's a node with A, so everything that starts with an A will be in the range of that subtree. And that comes before everything that starts with a B, which is in this subtree, and so on. All right, so there's an inherent connection between the suffix trees and ordering the suffixes, or sorting all the suffixes in the standard lexicographic order, at least if you draw the child edges in the right order. And so how about forgetting about this fancy tree with all its pointers and just keeping that sorted order? Sounds maybe a bit crazy because we've used a lot from the tree structure in these applications. But let's see how far we get. I'll call this L for leaves. So you should think of it basically as L of 0 is the index for this leaf, which always is the last. So in banana ban would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Hope that's correct. L0 would be 9 because the first leaf in lexicographic order is the leaf that has starting index 9 and so on. So you can represent this lexicographic ordering as just an array of numbers. Now, it turns out that's enough to do some of the questions, to answer some of the questions that we've answered before with the suffix tree. For example, we can still do string matching. If I have a pattern like Anna, how do I find the occurrences of that pattern in our text? I do a binary search in this sorted list. So how would binary search work? Well, we'd start in the middle. Now I would compare, is Anna smaller or bigger than this in alphabetic order? And okay, we straight bang into the special case. It depends now what I add to Anna at the end. Let's suppose I add the $sign. Then it would be smaller. So now instead of the whole range, I have this as the range of possibilities for the binary search. I compare it with the middle one. A and dollar is smaller. So now I'm in this range. And I would do another example, another comparison here. So I would find that if Anna dollar was in this list, it would go between those two. I could do a second, I don't know, Anna pound, where pound is bigger than all dollars. Of course, pound's bigger than dollars. If you do this binary search again, you would find that it should go in between here. What does that mean? It means all the words that start with Anna are between those two positions. And if I look in my array, what the numbers there are in this L array, it would be the starting indices of these suffixes, which is nothing but the occurrences, the first index of the occurrence of Anna. So by two binary searches, I can find all the indices where this string occurs. So I could do the same kind of trick as in the suffix tree, but without all the tree. I've not looked at all that stuff. I've forgotten all the pointers and all of the nodes. I just kept the sorted order of the suffixes. So that's a bit of my motivation for why you don't actually need much from the suffix tree for this application. So formally, the suffix array is just this list of indices, one array of numbers. I've explained this already, but here it's listed again. Note that it has indices from 0 up to n inclusive, because we add this dollar symbol, so we have n plus 1 characters in the text, right? Same as before. And yeah, to say it again, so the rth entry in the suffix array is the rth smallest suffix in lexicographic order. And what we have in the array is the starting index of that suffix. The algorithm that I sketched on the example for finding the occurrences of a pattern, it does 2 binary searches. Now you will remember binary search takes log n plus 2 if we want to be worst case on the safe side. Steps of recursing down until you found a position. But each of the comparisons can take up to m character comparisons. So the overall time is log n times m. Okay? And you should compare this. In the suffix tree, we had essentially m as our matching time. So we have a log n overhead, which comes from forgetting all of the tree. So in a way, I mean, it's not nothing, but log n is much, much smaller than n. So you could say that's tolerable to be a bit slower when now all you need is just an array of numbers and not this dozens times larger suffix tree. So as a first step, that already looks promising. And what I'll convince you in the rest of this unit is you can base on this suffix array, you can base all the algorithms that we've seen for suffix trees with a few extra tricks. You can simulate what they do with much less memory. Okay, there's a few nitpicks on the definitions that I'd like to hammer in. So as soon as this works. Yep, it's come up now. I'll leave it here, then you have the nice rendering. Actually, you can see the question. Maybe it's useful to keep that slide up, then you have the definitions there. I don't want to rush this question because there's a lot of insight to be had from that one. So take your time. Oh, we reached my magic threshold of 50 people. And we're still busy thinking. A few. Okay, let me start discussing so we don't overrun too badly. It's actually a lot of stuff is correct on this one. Okay, let's see. First of all, L lists the start indices of the leaves, or the start indices of the suffixes corresponding to the leaves in left to right order if we draw the tree in the normal way, where smaller goes to the left and larger goes to the right for each child. In my upside down world here, you have to kind of tilt your head to the left. Otherwise, this is correct. The path label here, it's not the leaf storing R, but it's the rth smallest leaf, or lexicographic order. So it's kind of the other way around, and this one is the right answer. Another way to say that same thing is if you take the suffix that starts at position L of R, then that's the rth smallest among those. The last is maybe, I don't know, maybe a bit surprising, but I think I've said it quite explicitly. Both the suffix array and the suffix tree take, under the assumption that the alphabet is constant, take a linear amount of space, theta of n words of space. But the constant for the suffix tree will be much bigger. And indeed, for the suffix array, the alphabet doesn't even make a difference. All that I'm storing is n numbers, n indices between 0 and n. So for the suffix array, the alphabet size is irrelevant, and for the suffix tree, that certainly plays a role. Right, and we've just seen both can be used to solve string text indexing or string matching. Text indexing is the same as string matching, but with the pre-processing on the text explicitly allowed. Okay. Maybe apart from the last question, most people agreed on this. So maybe it was just maybe it should have said string matching to be more clear. Now we've seen this suffix array could be useful, but how do we get it? That we still have to find out. One option is compute the suffix tree and then read off the order of the leaves. But we're trying to avoid to have these complicated construction algorithms for the suffix tree. So it would be a bit disappointing if we had to construct the tree as an intermediate step. Instead, we can go more directly by the definition. The suffix array needs all the suffixes in sorted order, so we might as well produce that by sorting. And we could just use any of the general purpose sorting methods. Unit 3 says hi. That's trivial to code up. You just have a comparison functions for strings. That's usually built into libraries anyways. So this takes 2 lines of code. Unfortunately, this is not so great because the comparison of any 2 suffixes could take a linear time. As often, if you take a boring text like everything is A's, that gives you the worst case for this stupid algorithm. If you're not careful, then that extreme case for a text will usually screw you over. And so while it's easy to code, it's worse than quadratic in the worst case. So that's not quite so great. And indeed, we can do better. We can do even better without going very far into the world of suffixes. The first thing I want to show you is just a general purpose method to sort strings. That's better than that, at least on average. Before we get to that, another short connection that it's worth making. This time it's unit 5 that says hi. That was the Burrs-Wheeler transform. And it's worth pointing out so in case of doubt, I wanna point out this says very easily, so it should be a trivial algorithm, both fast and conceptually super easy. That's important here because if you strike that out, it's possible either way by just computing it from scratch. But that's not the what the question is getting at. We passed the magic 50. So there's a roughly equal, not evil, split between options 2 and 3. Now things shift. Okay. Anyways, the majority is right. So here, it's true that you can compute the Burrs-Wheeler transform from the suffix array or from the suffix tree. The reason for that is if you have, let me show you the connection. So this is a slide I just borrowed back from Unit 5. Remember what the Burrs-Wheeler transform was doing is it takes all the cyclic shifts and sorts them. And then it takes this last column, that was the BWT. And to compute that, note when we do the sorting, we never have to look past the dollar symbol because the dollar symbol in all of the cyclic shifts occurs at a different position. So there's no way we'll ever get with our comparisons behind that. We would only get behind that symbol if there was the same dollar symbol in both strings that we're comparing. But that can never happen here. So in a way, sorting these cyclic shifts is the same as sorting just the suffixes. You don't see the slides. Didn't switch back in. That was what you were supposed to see. The Burrs-Wheeler transform takes all the cyclic shifts, sorts those, and takes the last column. That's exactly the slide from back then. And if you compare any of the two cyclic shifts, then you always stop comparing at the dollar symbol or earlier. You never go further because the dollar symbol is never aligned at the same position. And so sorting these cyclic shifts is the same as sorting the suffixes. The order will be exactly the same. And so if we have all the suffixes sorted, how do we get the BWT? The formal connection is here. I can take the position that is in the corresponding entry of the suffix array, and now I would want, instead of the starting index, I want the letter that is wrapped around and in the last column. that is actually the character that comes one before that character. So what I have to do is I subtract one and then look in the string or in the text. Maybe it should be, okay, so it was called the source text in Unit 5. So you look at the position that comes before that starting position of the suffix. That's how you can compute the Burrs-Wheeler transform in linear time from the suffix array. Now, the other direction seems unclear. Just because you have these characters, it's not, at least not very easy to figure out what the order of the suffixes should be. Okay. Yeah, I want to briefly show this sorting algorithm. There's no code, it's just an example, so we can go over this fairly quickly. It's not the most central thing. I just want to show, before we go to the more sophisticated algorithm tomorrow, for many cases you get with a simpler solution a fair bit. So think about the general problem. You're given a list of strings like these. How would you sort them efficiently? What's not so great an idea is to use comparison-based sorting, say merge sort or quick sort, as a black box. And whenever you need to compare two strings, you just do the comparison from start to beginning to the end. The reason that's not so great is if the strings agree on a long common prefix, you repeatedly scan that long common prefix, and you pay for that each time whenever you do a comparison. So the extreme case is, suppose all the strings start with some long prefix that is the same for all strings, and then they differ. Say you're sorting URLs and they're all within the university domain, then you would have that easily. And so there's an easy way to do better than that. And that is based on quicksort, but it takes advantage of the fact that we're sorting strings. And it works like this. We pick a pivot element, as always in quicksort, but we'll only look at the first character in this round. That's why these are highlighted. So the pivot character tells us there's words that start with a character smaller than this character, and those that start with a letter larger than that character, and those that start with that character. That's why it's called fat pivot, because there's a partition that has everything that's equal to the pivot according to the first character. Right? These have a starting character smaller than s, these larger than s, and these have s. Now the trick is, for all those that start with an s, I know that they all start with an s, so no need to look at that s ever again. Instead, I'll just remember, for these strings, the first character is definitely the same. Start looking at the second. That's the main trick. The way the example would continue, here you pick a pivot. Okay, it's this tiny example, so you just have these two sorted. Here it's more interesting. The pivot says I have h as the second character, so I split by the second character into those that have a character before h and after h, and those that have h. And again, for those that have an h as the second character, I know they have sh as the first two characters for all of them. Never look at them again. Okay? In the last example, we have the degenerate case that they are all equal. So I just read over all the t's, never look at them again. And there's no strings that have a smaller or larger character. These are done. These are sub-problems of size 1. For these, I pick another pivot, and I again have this degenerate case. They all have the same next character, so I just advance and never look at the e again. For these, I have some, excuse me, some that are smaller. No, these all have e, and one that's larger. So again, I never look at the e again. And here I just advance one more because the algorithm doesn't see it yet, but of course the strings are just the same. One more round here. Okay, L, I have 2 that start with L and 3 that are smaller. I guess you see how this continues. Now, the trick with all of those, okay, these continue for a while until they discover that indeed the two strings are the same. But if you analyze this globally, you never read for two strings, if they have some shared prefix, you never read that shared prefix twice. You only read it once. Because you always remember, if you go into this middle partition, you remember that they were the same. So when you discovered once that two strings have a common prefix, you're not going to look at it again. That's fat pivot radix quicksort. If you want to see the details and code and so on in more slow pace, it's in the red book that we used for other units. I'll skip the details for the code here, so you don't need to know that part. You can show that if the texts are somewhat random, this is a very fast method. It's also very simple to code and works well for many types of texts. It's still fairly slow if your text is completely degenerate. If your text is all A's, you would always have this middle partition, and you would read through the entire text, so it would be quadratic still. But you've reduced it for many more interesting cases where it's not suffixes of a text. This is a good method. Now, for the concrete case that we're concerned with, sorting the suffixes of a fixed text, we can do much better even in the worst case. And for that, we'll have to work a bit harder. And we won't do that tonight, but that's what's coming up.